Most of what people know about shrimp comes from a plate. The word itself does a kind of damage before any thinking begins. Shrimp are small things, soft and pale, paper-thin, and curled into a tight question mark on ice. They are sold by weight, 200 grams to a box, in supermarkets that smell faintly of the sea and mostly of refrigeration. A shrimp, in almost every kitchen in the world, is something that arrives already dead and unrecognizable, already part of the meal, already past being an animal. Almost no one has ever had to think of a shrimp as dangerous or fast or strange or anything other than something that ended up in a sauce. The animal we'd like to spend time with tonight is none of those things. It lives in shallow tropical seas. In burrows, it digs by hand into the sand and rubble of coral reefs, from the Caribbean to the Red Sea to the warm shallows of the Indo-Pacific. In most species, it is about 3 to 5 centimeters long, mostly transparent and mostly unremarkable to look at if you don't know where to look. But on one side of its body, on either the left or the right, never both, it carries a single claw that has grown to roughly half the length of its entire animal. Inside that claw sits a small mechanism, a plunger and a socket, evolved over the better part of 150 million years. When the shrimp draws that claw back and lets it fall, the closing takes about 600 microseconds, roughly 500 times shorter than the time it takes a human to blink. In that span, a jet of water shoots out from between the two halves of the claw at something like 25 meters per second. The water moves so quickly that it cannot stay water. A small bubble forms in its wake. Not air, not breath, just a region of near vacuum where the water has briefly torn itself apart from itself. A few microseconds later, the surrounding water rushes back in and the bubble collapses. When it does, the gas inside is squeezed so violently and so quickly that the temperature for a sliver of a moment far too short to feel climbs to somewhere close to the surface of the sun. A flash of light is released along with the collapse. You couldn't see it with your eyes. The flash lasts less than 10 nanoseconds, and it is faint, but it is real, and it has been measured under laboratory conditions. The physicists who first found it gave it a name. They called it shrimpoluminescence because no other animal had ever been observed making light in this way. Inside the claw of a creature that costs almost nothing at a fish market, every time it strikes, a small star is briefly lit and then extinguished. This is happening as you read this paragraph. The world's coral reefs are full of these animals, snapping a few times a minute apiece by the trillions. Each snap creates a tiny flash. The collective sound of all those snaps taken together is loud enough that during the Second World War, Navy sonar operators along the Pacific coast had to keep special charts of where the shrimp lived, because in shrimp territory, no sonar could clearly hear an approaching submarine. It is a strange thing to be told, this late in the history of natural science, that an animal most people have been eating without curiosity, their entire lives has been carrying physics of this kind in its right hand. But the science is settled. The high-speed cameras have been pointed at the claw. The hydrophones have been buried in the sand. The bubbles have been photographed in the half-light of their own brief burning. We know what these animals do. We are still, in many ways, trying to understand how. If a quiet room and a few hours sound right tonight, a subscribe helps the channel keep going. And in the comments, we'd be curious, had you ever heard of this animal before tonight? Or is this the first time anyone has told you that the shrimp in the supermarket has a cousin in the reef that strikes with the temperature of a star? Somewhere along a coastline you will probably never see, a pistol shrimp the size of your finger is pulling its claw back, holding it for a long second, and letting it fall. The water in front of it boils for a microsecond. A small star briefly catches and goes out, and the reef above does not register that it happened. The first time anyone in modern science took serious notice of a pistol shrimp, it was not on a reef. It was inside a submarine in the middle of a war. In the spring of 1942, in the waters off the Southern California coast, an American sonar operator on a training exercise reported a sound he could not identify. It was constant, irregular, and dense, a crackling rendered through his hydrophone as something between heavy rain on a tin roof and the sound of fat frying in a heavy pan. He did not know what was making it. He knew only that, while it lasted, his sonar was useless and submarines could approach through it unheard. The reports came in from every American naval base along the Pacific: Hawaii, the Marshall Islands, the Philippines, the warm shallows north of Australia. By 1943, the issue had become serious enough that the United States Navy convened a research program to figure out what the noise was and whether it could be predicted, avoided, or used. The listening section of the University of California's Division of War Research was assigned the question. They put hydrophones into shallow tropical water, dropped sealed jars to collect specimens from the seabed, and began identifying what was down there making so much sound. The answer, when it eventually arrived, was a small animal, a snapping shrimp a few centimeters long, living in colonies of hundreds of thousands across the shallow tropical seabeds the US Pacific Fleet was operating over, each one snapping its single oversized claw a few times every minute, day and night, year-round. Multiplied by an entire reef bed, the noise was loud enough to mask the sound of a ship's engines at close range. The Navy started printing charts marked with the regions where these shrimp lived in red, and the advice given to commanders was practical. If you wanted your sonar to function, you avoided those zones. If you wanted your submarine to disappear into static, you crossed them. By 1947, when the question was written up for the U.S. Naval Institute's proceedings, the wartime acoustic teams had a working understanding. Sonar operators carried hydrographic charts that showed bottom types, depths, and pistol shrimp grounds, all on the same map. What no one in the program seems to have written down in the formal record is the moment of recognition itself. The moment when a marine biologist or an acoustic engineer working under wartime urgency first looked at the recording, looked at the specimens in the jar and said, "It is a shrimp." The crackle that has been deafening the Pacific Fleet for 2 years is being made by an animal smaller than a finger. There are several reasons that recognition would have been hard to arrive at. The first is that in the shallow waters where these shrimp live, you cannot really see them. They spend most of their lives in burrows, hidden under rubble and coral, emerging mostly at night and only briefly. The second is that the sound a single pistol shrimp makes in air in a quiet room is not particularly loud. It is a sharp pop, similar to a finger snap or a small twig breaking. It does not announce itself as something an animal does. It announces itself as something that has fallen or broken, and most importantly, in 1944, no one understood the physics of how that sound was being made. The accepted theory at the time, and for the next half-century, was that the claw simply slammed shut hard enough to crack the water like a small whip. It was a respectable hypothesis. It was also wrong, and would remain in the textbooks until the year 2000. The practical problem was solved nonetheless. The shrimp went onto the maps, the fleet adapted to their territories, and the war moved on without resolving the deeper question of what these animals actually were. What the wartime program did not and could not study was how much of the ocean's real soundscape was being shaped by these animals at all hours, in all weathers, across every shallow tropical sea on the planet. That research would not begin in earnest until the 1990s, when underwater acoustic ecology became its own discipline. By then, the work had a different urgency. The reefs the shrimp had been quietly running for hundreds of millions of years were starting to go quiet, and the people listening were trying to understand what the silence meant. If you lower a hydrophone into a healthy Caribbean reef on a warm summer night, what comes through the headphones is something close to the sound of fat sizzling in a heavy pan, or steady rain falling on broad leaves. Not quite random, patterned, but at a rate the ear cannot easily resolve. In a single coral head, in the right conditions, the snap rate has been measured at 1 to 2,000 snaps per minute. Across a square kilometre of healthy reef, the snap rate climbs into the tens of millions per hour. Each snap is a single animal's single decision: hunt, defense, communication, territory. Together, those individual decisions make up the dominant biological sound in the high-frequency band of the entire shallow tropical ocean. Above a few kilohertz, nothing else really comes close. There is a more recent finding that changes the meaning of that sound. Coral larvae, the microscopic young of reef-building corals, drift through open water in their first few days of life looking for somewhere to settle and grow. The cues they used to choose a place were a mystery for a long time. Chemistry plays a role, light plays a role, but sound, it turns out, plays a much larger role than anyone had expected. In a series of studies published between 2016 and 2024, marine biologists at the Woods Hole Oceanographic Institution and elsewhere demonstrated that coral larvae actively prefer the soundscape of a healthy reef to the soundscape of a damaged one. When researchers broadcast healthy reef sound through underwater speakers placed at degraded sites, larval settlement rates climbed significantly. The larvae were not primarily listening for fish, they were listening for the snap of pistol shrimp. A healthy reef sounds like fat in a pan. A dead reef sounds like nothing. The larvae can hear the difference, and they go where the noise is. This means that, in a way, none of the wartime acoustic engineers could have imagined the shrimp on the floor of the reef are not only its hidden percussion section, they are also in part its recruiters. The crackle that interfered with the US Navy's sonar in 1944 had been calling young corals home for considerably longer than there had been a Navy. What the modern listeners do not yet fully understand is how all of this fits together. The snaps can be counted. They can be correlated with water temperature, with light, with season. In warm summer shallows, the rate climbs steeply. In winter, it falls to roughly 1/100th of its peak. The difference between a thriving reef and a dying one is now audible to anyone willing to lower a hydrophone. What cannot yet be said with confidence is what each individual snap is for in the moment it is made. A snap can be an attack, a warning, a courtship signal, a territorial assertion, or something else entirely. The animals making them are not asking us to understand. They have been doing this for considerably longer than we have been a species capable of asking. The oldest fossils we have of the family these shrimp belong to date to roughly 150 million years ago, in the warm, shallow seas of the late Jurassic. Dinosaurs were walking on the shorelines above. The corals of that era are mostly gone, replaced several times by different groups of corals as the planet cycled through extinction after extinction. But the shrimp in the rubble beneath the corals have continued through the death of the dinosaurs, through the rise of mammals, through every ice age and every long warming, snapping their small claws into the water of every shallow tropical sea on Earth, the entire time we have been here, and most of the time we have not. There is a paragraph in the methods section of a paper published in the journal Science in September of 2000 that mentions 7 small shrimp by species name. They are not described at any length, and they are not pictured. But for 50 years before that paper was published, every textbook in the world that mentioned them was wrong about something fundamental. And after the paper was published, every textbook had to be revised. And everything we now know about how these animals make their famous sound rests on what those 7 shrimp did in a tank in the Netherlands, in front of a high-speed camera over the course of a few hours one afternoon. For most of the previous century, the explanation for the snap had been the obvious one. 2 hard surfaces meeting at speed make a noise. The shrimp's claw has 2 such surfaces. The snap, therefore, was assumed to be the sound of the claw closing, the underwater equivalent of a wooden plank dropping flat onto a table, or a pair of castanets being struck together by a flamenco dancer's wrist. It was a reasonable hypothesis. It was held by serious people in the field, and it survived in the textbooks from the wartime acoustic studies of the 1940s through the popular natural history writing of the 1980s. The only problem with it was that nobody had ever filmed a closing claw slowly enough to actually check. The first person to suspect something was off was a biologist named Barbara Schmitz, working in the early 1990s at the Technical University of Munich. Schmitz had been keeping snapping shrimp in seawater tanks for behavioral studies, and over time she had noticed something the literature did not mention. At the instant of the snap, there appeared to be a tiny flash of light from the claw. It was not bright, and it was easy to dismiss as a reflection of the room lights or a trick of her own dark-adapted eyes. But it was persistent. She thought it was there every time. If the snap were really a mechanical click like a castanet, there should not have been any light at all. Castanets, after all, do not glow. What Schmitz suspected, but could not on her own confirm, was that the answer might lie in a physical phenomenon called cavitation, a process that had been studied for nearly a century, but mostly in the context of engineering, by people trying to keep ships from destroying themselves. To follow that idea any further would require working with someone who specialized in the strange things liquids do at high speed. In the late 1990s, Schmitz made contact with the fluid dynamics group at the University of Twente in the Netherlands. The group was led by a physicist named Detlev Lohse, who had spent the previous several years working on a closely related phenomenon called sonoluminescence, the emission of light from collapsing gas bubbles inside a liquid, a process that physicists could just barely reproduce in the laboratory, and which they understood, even then, only in outline. Lohse heard Schmitz out. The proposition that a small marine animal might be doing, casually, something that took a tuned ultrasound rig to reproduce in physics, that was worth a closer look. The experiment took shape over the next 2 years, with Lohse and Schmitz joined by 2 younger researchers at Twente named Michel Versluis and Anna von der Heit. 7 shrimp of the common Atlantic snapping species Alpheus heterocalis were collected and held in seawater tanks, then placed one by one into a small viewing chamber next to a hydrophone for the sound and a high-speed camera capable of recording at 40,000 frames per second. The lighting was dimmed to make any light emission visible against the background. The cameras were started, and then they waited for one of the shrimp to do, on its own time, what shrimp like it do every few minutes anyway. Pull its claw back into a cocked position, hold it for a moment, and let it fall. When the recordings were played back, slowed by a factor of more than 1,000, the team could see what nobody had ever quite seen before. The 2 halves of the claw, as they closed, did not strike each other with any real force. They came together quickly, but the motion was controlled, almost delicate, a small plunger on the movable half sliding precisely into a socket on the fixed half. As the plunger entered its socket, a thin layer of water trapped between the 2 was driven outward in a tight jet, at a speed measured at roughly 25 meters per second, or about 90 kilometers an hour. That is roughly the speed of a car on a city street, compressed into a stream of water no thicker than a grain of rice. At that speed, the water did something that water under ordinary conditions does not do. It briefly came apart from itself. The pressure in the wake of the jet dropped low enough that a small bubble of water vapor formed, lasted for a few hundred microseconds, and then collapsed back in on itself as the surrounding water rushed in to fill the space. The collapse was what made the sound. The claw had already finished closing by the time the noise occurred. The snap was not the claw at all. The snap was the bubble dying. And in the moment of collapse, a small flash of light was released, brief enough that no one watching with the unaided eye would have seen it. The faint flash Schmitz had been catching in her dark tanks in Munich half a decade earlier was real, and it had a name from a different branch of physics. Sonoluminescence, the emission of light from a violently collapsing cavitation bubble, was something that had been observed only inside carefully driven ultrasound chambers, in clean water under controlled laboratory conditions. It had never been observed coming from an animal. The shrimp, in the course of its ordinary feeding and territorial behavior, was producing the same effect in seawater on a coral reef without instruments. Versluis, Schmitz, von der Heydt, and Lohse published the main result in Science in September of 2000, and a year later, with a follow-up paper in Nature, the team established that the light was real, photometered it carefully, and gave the animal-produced version a name of its own to mark where it had come from. Shrimpoluminescence, they called it, half with a fluid dynamicist's sense of humor, half to register that it was, as far as anyone had ever shown, the only known case of an animal making this kind of light at all. The speeds in this account are easy to read past as numbers, but they are worth holding for a moment. The closing motion of the claw, from fully cocked to fully shut, takes about 600 microseconds, 6/10,000ths of a second. A human eye blink, by comparison, takes about 300 to 400 milliseconds, depending on the person. The shrimp can complete the closing motion of its claw roughly 500 times in the time it takes for one blink. Filming the snap at a speed that actually shows what is happening requires a camera capable of 40,000 frames a second, which, until fairly recently, was a piece of equipment most biology departments did not have access to. The snap had been mysterious for as long as it had been because the tools required to see it clearly had not existed yet. What the Twente experiment answered was the central question. What it left open and what other groups have been refining ever since, most prominently the lab of Sheila Patek at Duke University, which has spent years working out the mechanics of fast biological movement, is the harder problem of how exactly the claw stores enough energy in its cocked position to deliver a closure at those speeds at all. The current understanding is that the claw is a kind of biological spring, held under load by a small set of adhesive surfaces and a particular geometry of the joint that allows the muscle to slowly build tension against a latch, and then, when the latch releases, deliver all of that stored energy at once, faster than any muscle could ever move on its own. It is the same general trick that the mantis shrimp uses for its strike, that trapjaw ants use for their mandibles, that chameleons use for their tongues. All of these animals have, separately and independently, evolved their way into the same physical solution. The pistol shrimp's version is among the most extreme of them. The 7 shrimp in the viewing chamber at Twente were never given names. They appear in the methods section of the paper only as a group by species, with notes on their size and origin. Most of them, in the way of small invertebrates kept briefly for an experiment, would not have lived long after the work was finished. There are no portraits of them. They have no stories that the literature has chosen to tell. But for half a century before that one afternoon, every textbook in the world said the snap was the sound of two hard surfaces meeting, and after that afternoon, every textbook had to be redrafted. The shrimp themselves never knew. The work they did in front of the camera that day was the same work shrimp like them have been doing every day, in every shallow tropical sea on the planet. And the only difference on this one afternoon was that the camera was finally fast enough to see it. A common version of this story, repeated in nature documentaries and popular science articles for the last 20 years, goes something like this. When the pistol shrimp closes its claw, the bubble it creates collapses with such force that the inside of the bubble briefly becomes hotter than the surface of the sun. The version is striking, easy to remember, and almost right. It is also, in the most literal way, wrong in one specific number, and the correct version of the number is the more interesting of the two. The actual measurement, which comes from the same Twente and Munich collaboration that worked out the cavitation mechanism in 2000, places the temperature inside the collapsing bubble at somewhere around 4,700 degrees Celsius, give or take. The surface of the Sun, by the most careful astronomical measurements, sits at about 5,500 degrees Celsius. The bubble, in other words, is not hotter than the surface of the Sun. It is slightly cooler, by about 800 degrees, in the same way a hot oven is cooler than the inside of an active volcano. The two numbers are close, but they are not the same, and the close but not the same is the thing worth pausing over. What the shrimp is doing in the small enclosed space inside a collapsing bubble of water vapor is reaching a temperature on the order of the photosphere of an average yellow star. It is doing this with a piece of itself the size of a fingernail clipping in shallow tropical seawater several hundred times a day. The original claim that this temperature exceeds the Sun has been repeated often enough that it now exists as a kind of folk fact, and the corrected version sounds, at first, like a diminishment of the wonder. It is not. The corrected version is the more surprising of the two, because once you start asking how a small marine animal arrives in the neighborhood of stellar surface temperatures at all, the explanation takes you somewhere quite far from biology. The physics involved is a process called adiabatic compression, and it is one of the more counterintuitive corners of classical thermodynamics. When a gas is compressed slowly, heat can flow out of it into the surrounding environment, and its temperature rises only modestly. When a gas is compressed quickly, heat does not have time to escape, and the temperature of the trapped gas climbs steeply with the compression. This is the principle that diesel engines run on. A diesel cylinder draws in air, then a piston compresses that air so rapidly that the air alone, without any spark, reaches a temperature high enough to ignite the fuel that is then injected into it. The compression ratios involved in a diesel engine are modest, perhaps 15 or 20 to 1, and the resulting air temperatures are in the range of 500 or 600 degrees Celsius, hot enough to ignite diesel fuel, not hot enough to do anything dramatic. The collapse of a cavitation bubble is the same process, taken to a different scale entirely. The bubble formed in the wake of the pistol shrimp's jet starts at a diameter of roughly 3 or 4 millimeters, full of water vapor at near zero pressure. The surrounding seawater at ordinary atmospheric pressure, plus the pressure of the water above it, rushes inward to fill the space. The bubble's volume drops by something close to a factor of 1,000 in a few hundred microseconds. By the time the inrush is complete, the small remainder of gas trapped at the center is squeezed under conditions roughly equivalent to atmospheric air being suddenly compressed into 0.1% of its starting volume in less than 1,000th of a second. There is nowhere for the heat to go on that timescale, and so it stays in the gas. The temperature climbs steeply, the pressure climbs steeply with it, and for a small fraction of a microsecond, the conditions inside the remaining pocket of gas reach the territory where ordinary atoms begin to come apart. At those conditions, the gas is no longer behaving like a gas in any ordinary sense. The electrons in the outer shells of the atoms have enough energy to leave their atoms entirely. The gas becomes a plasma, a state of matter in which the particles are no longer neutral atoms but rather a mixture of free electrons and stripped, positively charged nuclei. Plasma is the fourth state of matter after solid, liquid, and gas. It is what stars are made of. It is what fluorescent tubes contain, what lightning briefly becomes, what the interior of a fusion reactor is engineered to produce, and for a fraction of a microsecond, inside a bubble smaller than a peppercorn. In shallow water off the coast of any tropical reef on the planet, plasma is what the inside of a pistol shrimp's strike contains. It does not stay that way for long. The collapse rebounds, the gas re-expands, the temperature crashes back down to seawater ambient within microseconds, and the bubble is gone. But while the plasma exists, it radiates light, in the same way any sufficiently hot gas radiates light. This is the flash that Barbara Schmitz first noticed in her tanks in Munich in the 1990s, and which the Twente group photometered carefully in their 2001 paper in Nature. The total energy of the flash is small, somewhere around 50,000 photons in less than 10 nanoseconds, far below the threshold of the human eye, requiring a sensitive photomultiplier tube to detect at all. But it is light, and its spectrum is the broad, continuous spectrum of a hot ionized gas, which is the same general kind of spectrum a star produces. The mechanism by which the light is generated has been worked out in some detail by the sonoluminescence community over the past 2 decades. Most of it comes from a process called Bremsstrahlung, a German word meaning roughly breaking radiation. When a free electron passes near a positively charged ion in the plasma, the electric force from the ion deflects the electron's path, and the change in the electron's motion releases a small amount of its kinetic energy as a photon. Across the trillions of electron-ion interactions happening inside the bubble in that microsecond, the integrated effect is a brief, faint flash of broadband light. The same process, scaled up by factors no one in this story is comfortable thinking about for long, is part of what makes stars shine and part of what would make fusion reactors visible if any of them were ever held stable enough to be looked at directly. What this means for the shrimp itself is essentially nothing. The flash, in biological terms, is a side effect. The shrimp is not using the light for anything. It cannot see the flash, and even if it could, the flash is over before any nervous system in the world could respond to it. What the shrimp is using is the shockwave that travels outward from the collapse, the pressure pulse that, when it meets the body of a small fish or crab in front of the burrow, can damage soft tissue badly enough to stun or kill. The light is a free thermodynamic byproduct of the process that produces the shockwave. The shrimp gets the kinetic effect it needs to feed. The plasma, the photons, the brief astronomical conditions inside the bubble, none of these are part of what the animal is doing from its own point of view. They are part of what physics does when an animal asks it for a shockwave and does not specify how to deliver one. That is, in a way, the strangest part of the whole arrangement. The pistol shrimp has not evolved to produce plasma, or to produce light, or to participate in any of the extraordinary physics inside the bubble. It has evolved to produce a fast-closing claw, which produces a fast jet of water, which produces a transient region of low pressure, which produces a bubble, which inevitably collapses under the surrounding hydrostatic pressure. Once the chain of cause has been set in motion at the level of the muscle, everything downstream happens because the laws of fluid dynamics and thermodynamics require it to happen. The shrimp is, in this sense, less the author of the physics than the trigger for it. It pulls the lever. Physics does the rest. There is a small humbling in that, if you sit with it for a moment. The most astonishing thing the animal does is also the thing it is least responsible for. The pistol shrimp has evolved the mechanism, the claw, the muscle, the latch, the geometry that allows the jet to form at the right speed, and the rest of the show is what water is and what gas does when it is squeezed quickly in the universe we happen to live in. The same physics, scaled differently, is what powers the cores of stars. The shrimp has, without knowing it, evolved a small handheld access point to the same general corner of the natural laws that runs the sky. Somewhere on a reef tonight, in a body the length of a thumb, something close to the surface of a star is being kindled and snuffed out several times a minute by an animal that has no idea what it is doing. If you look closely at a pistol shrimp from the front, and you have to look very closely because they are small and most of the time their heads are tucked into the entrance of a burrow, you will notice something on top of the head that does not appear on most other shrimp. Just above the eyes, the carapace, which is the hard shell that covers the front part of the body, extends forward and slightly downward into two small transparent shields, one over each eye. They are not opaque, they are not pigmented. They look in the way of biological structures whose function is not yet known, slightly ornamental, like a feature an artist might have added for symmetry. Crustacean taxonomists noticed them long ago and gave them a name. They are called orbital hoods, and for most of the 20th century, nobody could say with any confidence what they were for. The leading theory in the field guides and the textbooks was that they were a protective structure for the eyes, that they kept sediment out, perhaps, or shielded the eyes from incidental damage during burrowing or fighting. It was a reasonable guess. Many small animals that spend their lives in coarse substrate have some equivalent piece of armor over their visual organs. But the word reasonable here is doing a lot of work. Nobody had actually tested it. The hoods are transparent, which seemed to support the idea that they were not interfering with vision, but no one had carefully measured whether the shrimp could in fact see well through them, and no one had carefully measured whether anything was actually being kept out by them. And no one, and this is the strange part, had really stopped to consider the most obvious threat to a pistol shrimp's head, which is the pistol shrimp itself. The animal carries one of the most powerful shockwave generators in the natural world, about 3 centimeters in front of its own eyes. Every time the claw closes, the collapse of the bubble releases a pressure pulse that propagates outward through the surrounding water at the speed of sound in that medium, which is a little over 1,500 meters per second. That pressure pulse is the entire point of the weapon. It is what stuns the small fish or crab that has wandered too close to the burrow entrance, and it is strong enough to be dangerous to a soft-bodied animal positioned anywhere in front of the claw at the moment of the strike. The shrimp's own head is positioned, by anatomical necessity, exactly there. The shrimp is firing a small underwater blast wave at point-blank range several times a day in the direction of its own brain. This was the question that the biologist Alexandra Kingston and her colleagues at the University of Tulsa and the University of South Carolina took up in the late 2000s. Why does a snapping shrimp not seem to suffer any obvious neurological damage from its own strikes? The literature on blast injuries in vertebrates was, by then, a substantial body of work, much of it driven by the medical attention given to traumatic brain injuries among military personnel exposed to improvised explosive devices in Iraq and Afghanistan. The general picture from that work was clear. A shockwave that travels through water or air at high amplitude, when it crosses into living tissue, transfers some of its energy into the cells it passes through, and the result, depending on the magnitude of the wave, ranges from mild concussive symptoms to severe and permanent damage. A shrimp firing a blast wave a few centimeters from its own eyes should, by any straightforward reading of that physics, be punch-drunk within hours and dead within days. But shrimp in the laboratory snap thousands of times across a healthy adult life and show no obvious sign of impairment. Something was protecting them. Nobody knew what. The Kingston group designed a series of experiments that, in retrospect, look almost startlingly straightforward. They took specimens of the common Atlantic snapping shrimp, Alpheus heterocalis, the same species the Twente group had used, and carefully removed the transparent orbital hoods from one group of them, leaving a control group with hoods intact. Then they exposed both groups to the kind of shockwave a snap produces, generated under controlled laboratory conditions, and they watched what happened. The results came out in 2022 in the journal Current Biology, and they were unambiguous. Shrimp with intact orbital hoods, after being exposed to a single representative shockwave, behaved normally. They moved toward shelter at the speed they always did. They oriented themselves with no apparent confusion, and their motor control was unaffected. Shrimp with the orbital hoods removed after the same exposure were noticeably impaired. They were slower to find shelter. Their swimming was less coordinated. Some of them showed what looked like the small invertebrate equivalent of disorientation. The hoods, in other words, were not ornamental. They were not primarily about keeping sediment out of the eyes. They were doing something much more specific and much more strange. They were absorbing the shockwave. To confirm what the behavioral evidence suggested, the team placed sensitive pressure sensors on the outside surface of the hood and beneath it, near the actual position of the brain inside the carapace. They had a shrimp fire its claw, and they recorded what the pressure pulse looked like on the outside of the hood and what it looked like by the time it had passed through. The pressure measured under the hood, near the brain, was significantly lower than the pressure measured outside it. The hood was attenuating the shock wave, not perfectly, but enough to bring the energy reaching the soft tissues of the head down into a range that the animal could tolerate indefinitely. The mechanism, which the team worked out by sealing the hood's openings and rerunning the measurements, depended on small gaps at the front of the hood. As the shock wave struck, water inside the hood was pushed outward through those gaps in a controlled way, and the kinetic energy of the pulse was converted into the kinetic energy of moving water and dissipated outward, away from the head, rather than being transmitted inward to the brain. When the paper was published, the result was framed in the language Kingston's group had been careful about. Orbital hoods were, on the available evidence, the first biological armor system known to function specifically as a shockwave damper. Not the first armor. Animals have evolved hard surfaces and protective shields many times in many lineages for many reasons. But the first known case of a hard biological structure whose particular geometry was solving the very specific problem of attenuating a high-amplitude pressure pulse and protecting the soft tissue behind it. Engineers working on helmet design for military and medical applications took an interest almost immediately. A follow-up paper, published in 2025, examined whether the same hoods that protected the brain also impaired the eyes underneath them, and found that they did not. The hoods are transparent enough at the relevant wavelengths that the shrimp's already modest visual capacity is essentially unchanged by their presence. What the discovery did was to add a quiet correction to the story of the snap itself. For a long time, the snap had been framed in popular telling as a kind of free weapon, a free piece of physics the shrimp had stumbled into, costing nothing, doing nothing but harming whatever was in front of it. The orbital hood is the cost. The shock wave is not free. It is so dangerous, even to the animal that produces it, that the evolution of the snapping mechanism required the parallel evolution of a custom-built shock absorber on the animal's own face, and the two structures must have co-evolved in some careful relationship over a long span of time, because a shrimp that develops the snap before it develops the hood would not survive its own first strike, and a shrimp that develops the hood before it develops the snap would have invested in armor against a weapon that did not yet exist. How the order actually unfolded is a question that paleontology has not yet been able to answer, in part because the soft, transparent tissue of an orbital hood does not fossilize well, and the calcified fingertip of an old snapping claw, which does fossilize, tells us only that the claw exists, not what was on the head of the animal that carried it. The shrimp's eyes themselves behind the hoods are not particularly well developed. They are simple compound eyes, capable of detecting light and rough movement, but not much more. The pistol shrimp is not an animal that lives by sight. It does most of its work in dim light or in total darkness, inside a burrow or under coral rubble, and it relies on a different set of senses entirely to know what is happening in the world around it. The orbital hood, then, is not protecting an organ of fine perception. It is protecting an organ that has been allowed, over evolutionary time, to become almost vestigial, because the animal has moved most of its sensory effort somewhere else. The somewhere else, in this case, is a pair of long, thin antennae that extend forward from the head and reach into the surrounding water, like the white whiskers of a careful cat. Through those antennae, the shrimp tastes the chemistry of the water, feels every minor current, registers vibrations from approaching animals at distances of several body lengths, and, in the case of the species that have entered into close partnerships with other animals on the reef, maintains continuous physical contact with their partners through long, light touches that function as a form of language. That is, in a sense, what the orbital hood makes possible. By absorbing the shockwave at the level of the head, it allows the rest of the animal, the antennae, the nervous system that interprets what they bring in, the small body coiled in the burrow behind them, to keep functioning across thousands of snaps over a working lifetime. The hood is what permits the rest of the shrimp to do everything else it does. Without it, the snap would still work, but the animal making the snap would not last long enough to use it again. A few meters down from a sun-warmed surface in the northern Red Sea, on a stretch of sandy seafloor not far from a fringe of coral, there is a small round hole in the sediment. The hole is about the diameter of a pencil. Just outside it, motionless and bright in the filtered light, sits a small fish, no longer than a finger, its pectoral fins held lightly against the sand, its eyes scanning a half circle of water in front of it with the steady mechanical attention of a sentry. Behind the fish, half in shadow and half out of the burrow, is a pistol shrimp. The shrimp is carrying small loads of sand with its smaller claw, depositing them just past the entrance, then turning and returning into the burrow for more. While it works, one of its long white antennae rests, lightly and without any apparent effort, against the fish's tail. The antenna does not grip. It is not holding the fish in place. It is simply touching it, the way a person walking through a dark room might keep one finger trailing along a wall. This is the most thoroughly described partnership in the entire snapping shrimp literature, and possibly one of the most thoroughly described examples of interspecies cooperation in the whole of marine biology. It involves two animals from two completely separate vertebrate and invertebrate branches of life. They share a single burrow. They divide the labor of survival between them. They communicate, when communication is necessary, through a vocabulary of tactile signals that has been worked out over film, frame by frame, in a series of careful studies that began more than half a century ago and has been continuing in different laboratories around the world ever since. The principal early worker on the question was an Israeli zoologist named Ilan Karplus, who started studying the relationship in the warm, shallow waters of the northern Red Sea in the 1960s and 1970s. Carplus did most of his observations in artificial burrows constructed in glass-sided tanks so that the entire interior of the home could be filmed at high resolution while the animals went about their normal routines. In a 1979 paper published in the journal Zeitschrift für Tierpsychologie, he reported the first detailed frame-by-frame breakdown of how the two animals actually talk to each other. The shrimp, he wrote, maintains nearly continuous antennal contact with the fish whenever the shrimp is exposed at the burrow entrance or moving in the open. When the fish detects an approaching threat, a predator, an unfamiliar fish, anything moving toward the burrow at speed, it produces a series of rapid flicks with its tail or its pectoral fins. The flicks are transmitted up the length of the antenna to the shrimp, and the shrimp responds by retreating into the burrow. If the threat is judged minor, the signal is a low-amplitude wave of flicks at a slow rhythm. If the threat is serious, the goby dives headfirst into the burrow and the rate of flicking spikes sharply just before the dive. The shrimp, in either case, has responded and disappeared by the time the danger has arrived. Carplus also showed something else, which is the part of the story that is easy to miss on a first read. When the antenna is not in contact with the fish, no warning is issued at all. The goby will see the predator, will register the threat, will respond by diving into the burrow. But it will not on its own send any signal. The flicks are not a generic alarm display. They are a directed message requiring physical contact, and they are produced only when there is a specific recipient at the other end of the antenna who can receive them. The fish, in other words, is not warning the world, it is warning its shrimp. 3 things follow from that one observation. The first is that the system is mutual in a way most popular descriptions of the partnership get backwards. The conventional summary, repeated in nature documentaries and field guides for decades, has tended to describe the relationship as one in which a more or less helpless shrimp shelters in its burrow while a sharp-eyed goby acts as its guard. The framing has the politeness of a fable: small protected animal, vigilant friend, picturesque cooperation, and it places the shrimp, by implication, in the weaker position. The actual relationship is closer to the other way around. The shrimp digs the burrow, maintains it through hours of work every day, defends the structure with a weapon capable of stunning a fish, and provides the goby with shelter that the fish itself, on the open sand, would not have. The goby, in exchange, provides one specific service that the shrimp cannot perform for itself, which is to look out at the world. The trade is muscle and architecture for eyes. The second thing that follows is that the cliché, in its other common form, has the visual handedness of the two animals reversed as well. It is not unusual to hear the partnership described as one in which a blind goby is protected by a sharp-clawed shrimp, or in which the two animals split the work of vision somehow evenly. Neither is right. The pistol shrimp, as has been established by anatomical study going back well over a century, is functionally near blind. Its compound eyes are present and they detect light and rough motion, but they cannot resolve a predator at a useful distance. The goby's eyes, by contrast, are excellent. The family it belongs to is one of the best-sighted small fish in the reef community, with sharp resolution and a near full hemisphere of forward and lateral vision. The partnership exists because the shrimp cannot see and the goby can. To swap them in the telling is to misunderstand the entire arrangement. The third thing is the most interesting, and it is the one that does not survive contact with the casual version of the story at all. The communication system involved here is older than almost anything one might naively compare it to. The same general pattern, antennal contact, tail flick warning, controlled retreat, has been documented in shrimp-goby pairings across the Indo-Pacific, the Red Sea, the Western Atlantic, and the Caribbean. The species change. The cast is different from reef to reef, but the protocol is recognizable across every documented pairing, regardless of which species of shrimp is involved and which species of goby. A study published in 2022 looked at the molecular phylogeny of the goby genera that participate in this system and concluded that the warning signal behavior is shared widely enough across the lineage to have been present in their common ancestor, meaning the partnership, in something like its current form, has been operating in the world's reefs for at least tens of millions of years and probably considerably longer. Whatever else one might say about it, this is not a recent or fragile arrangement. It is one of the older working friendships in the ocean. What the partnership feels like from inside is something none of us will ever directly know. But the architecture of how it works can be reconstructed from the films, and there is one detail about it that is worth lingering on. The antennal contact between the shrimp and the goby is not occasional. It is the default state of the relationship whenever the shrimp is in any way exposed. The shrimp, going about its daily work, scooping sand, cleaning the burrow entrance, foraging for small food items at the threshold, keeps one antenna in light contact with the fish at essentially all times. The contact is delicate enough that the fish does not seem to mind. The fish is free to look in any direction it likes. The shrimp does not control where the goby is looking or how. The shrimp is simply available, listening through the long, thin filament of its antenna, ready to receive whatever the fish has to communicate for the entire duration of every moment in which the shrimp is outside the safety of the burrow it has built. To describe this as a relationship is not, in any of the loose senses, sentimental. The animals are not friends. They do not, as far as anyone can tell, recognize each other as individuals across long separations, and they will accept new partners if their original partner is lost. What they have evolved together is a working communicative protocol, a kind of underwater handshake that allows two animals from two enormously different parts of the tree of life to share a small contested patch of sand on a tropical seabed and keep each other alive in it. The protocol is what the relationship is. There is no warmth in it that we would recognize as warmth. There is something else, which is older and quieter and probably more durable than warmth. A long-established mutual usefulness, encoded into the morphology of antennae and the timing of tail flicks that has held up across geological spans of time and continues to hold up tonight, in countless burrows along every shallow tropical coastline on the planet, between countless small animals who have never been told what they are doing and who do it anyway, perfectly, on the schedule they have always kept. Imagine a small crab, perhaps the size of a thumbnail, picking its way along the floor of a shallow reef at dusk. It is moving slowly, with the side-to-side gait that small crabs use over uneven sand, and it is not in any obvious distress. A few centimeters ahead of it, in the shadow of a piece of broken coral, there is an opening in the substrate that the crab has not noticed and has no particular reason to notice. The opening is the entrance to a burrow. Inside the burrow, just past the mouth and entirely hidden from view, is a pistol shrimp that has been registering the vibrations of the crab's footsteps for the last several seconds through the long, thin antennae that extend out into the water column beyond the lip of the burrow. The shrimp has already cocked its claw. It is now waiting for the crab to walk into the small zone of water directly in front of the burrow entrance, the zone where its weapon can be brought to bear at the right angle. The crab continues to move. The shrimp continues not to move at all. The interval between the moment the crab is in range and the moment the shrimp's claw begins to close is, as far as anyone has been able to measure it, less than the time it takes for a single nerve impulse to cross a few centimeters of crab anatomy. The strike, when it comes, looks from the outside like almost nothing. There is a small disturbance in the water in front of the burrow. The crab, which a moment before was walking, is now lying on its side, motionless. The pistol shrimp is already extending out of the burrow, the smaller claw, the manipulator, the one not used for the strike, reaching toward the prey. The shrimp pulls the stunned crab inside. The sand at the burrow entrance settles. The reef on every side goes on as if nothing had happened. Inside the burrow, in the privacy of a tunnel system the rest of the world cannot see, the shrimp will spend the next several hours processing what it has caught. This is, in outline, how most predation by pistol shrimp works. The animal does not chase. It does not stalk in any extended sense. It builds a burrow at a location that is likely to see traffic, at the edge of a sand flat near a coral head, along a slope where small invertebrates and fish move past on their daily routines. And it waits, antennae extended into the water, for something edible to come close enough to be reached. The hunting is largely the burrow doing the work. The shrimp's contribution is to maintain the location, keep the entrance clear, and be ready at any moment to release its claw. Pistol shrimp will also, on occasion, leave the burrow and forage actively in the surrounding rubble, but the dominant pattern is ambush from inside a structure they have built and maintained themselves. The burrow itself is, by any reasonable accounting, the most important single thing in the animal's life. It is the shelter from predators, the hunting blind, the temperature buffer, the breeding chamber, and the only patch of the entire ocean in which the shrimp can be said to live in any meaningful sense. The construction of one of these burrows by an animal weighing less than a few grams, working alone with the smaller of its two claws, is considerable engineering. A mature burrow can extend 20 to 30 centimeters into the sediment, sometimes more, with multiple chambers, a primary entrance that is kept rigorously clear of debris, and in many species, a secondary back exit that allows escape in the event that the front entrance is compromised. The walls are not simply scooped out of loose sand. The shrimp packs the inner surface with smaller particles, often binding them together with mucus secretions from its own body, producing a tunnel structure that holds its shape against the slow shifting of the surrounding seabed. This work is continuous. Sand fills back in, currents reshape the entrance. The shrimp spends a substantial fraction of every day repairing and re-excavating. It is, in effect, a very small mason, building and rebuilding the only home it has ever had. What the burrow does for the larger reef, almost as a side effect, is something the reef cannot easily replace. Every gram of sediment the shrimp moves passes through its burrow and is redeposited at the entrance, where currents pick it up and carry it back into circulation. Across thousands of burrows in a single hectare of reef, this adds up to a steady, low-grade turning over of the seabed, a biological process that ecologists call bioturbation, and that plays a serious role in the cycling of nutrients in reef systems where nutrients are otherwise scarce. The shrimp is not aware of doing this. From the shrimp's point of view, it is simply maintaining the entrance to its home. From the reef's point of view, the shrimp is one of the chief reasons the seabed beneath the corals is not a static, oxygen-starved layer of compacted sediment, but a living, mixing matrix that supports everything else above it. There is one more aspect of the daily life of these animals that, until quite recently, was not widely appreciated outside the specialist literature, and that is worth pausing on. A surprising number of pistol shrimp species, including the well-studied Atlantic species Alpheus heterocalis, do not live alone. They live in long-term socially monogamous pairs. A male and a female share a single burrow, defend it together against intruders, and remain associated with each other across multiple molting cycles, which, in animals that reach sexual maturity in a matter of months and live for perhaps 3 to 4 years in the wild, can represent a substantial fraction of the entire adult lifespan. The biology of how this arrangement is maintained has been worked out over the last 20 years, principally in the laboratories of Melissa Hughes and a number of collaborators across the eastern United States. The picture that emerged from that work is more interesting than the usual 2-line summary suggests. In most Caridean shrimp, including the great majority of the snapping shrimp family, females are receptive to mating only briefly, for a window of a few hours immediately after their periodic molt, when the new exoskeleton has not yet hardened. Outside of that window, no mating is possible. The molt itself, in most species, is not externally visible until it is too late for an unfamiliar male to arrive in time. This is the structural fact that the monogamous pair bond appears to have evolved against. By staying with a particular female across her entire intermolt cycle, a male is in position the moment she becomes receptive. By staying with a particular male across the same cycle, a female has the protection of a partner with a snapping weapon during the few hours in which her own armor is too soft to defend her. The bond is mate guarding from one side and bodily protection from the other. Both halves of the arrangement reinforce the other, and across many generations the system has settled into a stable equilibrium in which neither sex does better on average by breaking the pairing and seeking new partners than by keeping the one they have. Once the pair has formed, the two animals share the labor of the burrow more or less evenly. Both partners excavate. Both partners defend the entrance against intruders, though the snapping claw is usually held by the male in the species that have been most carefully studied, and the bulk of the heavy strike defense comes from him. Both partners forage. Food that one partner brings back to the burrow is shared with the other, and the sharing is not casual. Recorded observations in tank studies show that the resident partner will accept food at the entrance from the foraging partner and bring it inside, where the two consume it together. The carpless literature, the same body of work that originally documented the antennal communication with the gobies, also includes descriptions of how a paired shrimp differs from a solitary one in the daily rhythm of activity. The paired animals are less restless, more efficient with their time, and more successful at retaining their burrows against the steady pressure of other shrimp trying to take them. The pair, as a unit, is harder to dislodge from a chosen location than either animal would be alone. There is one further finding from the more recent literature that gives the pair its full weight. A study published in the early 2000s, looking specifically at pair recognition in Alpheus heterochelis, showed that members of an established pair could distinguish their own partner from an unfamiliar shrimp of the same sex and similar size, and that paired animals reunited more quickly after separation than they did with strangers. The shrimp, in other words, know each other. Whatever the experience of that knowledge is from the inside, the behavior is clear at the outside. A long-paired male and female, separated by an experimenter and then returned to the same tank, will find each other and reoccupy a shared burrow with a speed and reliability that no random pairing of two strangers ever shows. They are not mating for life in any romantic sense. Both animals will accept a new partner if the original is lost, but for as long as both are alive and in proximity, the bond holds. In the wild, it can hold for the better part of the available adult life. What that means, taken alongside the burrow and the hunt and the antennal communication with the goby, is that the pistol shrimp is engaged in something considerably more elaborate than its general reputation has tended to suggest. It is a builder, a hunter, a partner, and a host. It has a home it has made by hand, in many cases shared with a fish whose vocabulary of warning signals it has co-evolved into, and in many cases also shared with another member of its own species who knows it as an individual and stays with it across the working years of its life. None of this fits easily inside the popular image of the animal as a small, twitchy creature with a disproportionate weapon. The weapon is real. The rest of the life, which is much harder to see from the outside, is what the weapon was developed to defend. On the lee side of a small Caribbean cay, in water shallow enough that an adult can stand on the seabed with their head and shoulders above the surface, there is a dull red sponge growing on a piece of dead coral rubble. It is roughly the size of a large grapefruit, with a soft, irregular outer surface and a few darker openings near the top, through which water moves slowly in and out under the rhythm of the tide. To anyone who has not been told what to look for, it is one of the more forgettable objects in the visible reef. Sponges of this general appearance can be found across the warm shallows of the Western Atlantic, attached to almost every available solid surface that is not already occupied by something more aggressive, and most divers pass them without noticing. The sponge does not move, it does not flash any color. It has no obvious features that a casual eye would interpret as biologically interesting. It is, in the unhurried language of the older marine biologists, simply substrate. If that sponge were carefully cut open along its longest axis with a sharp blade, something that has been done methodically by every researcher who has worked on the animals in question, because there is no other way to see what lives inside, the interior would not look like a single mass of soft tissue. It would look like a city in cross-section. The body of the sponge is structured around a network of internal canals and chambers, the largest of which can be several centimeters across, branching and rebranching through the interior like the tunnels of a poorly planned subway system. These canals are how the sponge moves seawater through itself in order to feed. Microscopic cells lining the walls of the canals beat tiny whip-like flagella in a coordinated rhythm, pulling water in through the smaller entry pores, drawing it through the labyrinth of the interior and expelling it through the larger upper openings called oscula. A single sponge of this size pumps a volume of seawater through itself every day that is many times its own body weight. What the sponge does not do, and what no one who designed the canal system in evolutionary time appears to have intended, is provide a perfect set of pre-built tunnels for an animal that would like to live somewhere structurally protected and physiologically buffered from the outside world. The canals are exactly the right diameter for a small crustacean. The walls, made of the sponge's own collagen and silica matrix, are sturdy enough to support occupants without being so dense as to seal off movement between chambers. The water flowing through the system is constantly oxygenated, constantly bringing in nutrients, and constantly carrying away waste. From the point of view of an organism small enough to fit inside, the sponge is the equivalent of a furnished apartment building with central air conditioning, free meal delivery, and an automatic plumbing system, the entire complex installed on the seabed of a tropical reef and requiring no rent. A very specific group of pistol shrimp has, over the course of perhaps the last 50 to 70 million years, learned to take advantage of this fact. They belong to the genus Synalpheus, a name that means, more or less, together with the Alpheus, signaling its close kinship with the better-known burrow-dwelling shrimp that have occupied the previous chapters of this account. There are something on the order of 160 described species of Synalpheus in the world's tropical seas, and possibly considerably more that have not yet been formally named. Many of them live the way most other pistol shrimp do, in burrows in sand or coral rubble, in pairs or small loose groupings, but a particular subset of them, concentrated mostly in the Western Atlantic and especially in the Caribbean, have made a different choice. They live inside sponges. They live there their entire lives. They do not, except as drifting larvae in the first hours after hatching, ever leave. The shift, in the long view, is not biologically trivial. To move from a burrow that the animal builds and maintains by hand into a pre-existing host structure that the animal merely occupies is to give up one form of work in exchange for taking up a different one. The Synalpheus species that live inside sponges spend a substantial part of their time defending the sponge from other organisms that might also like to use it, and from competing populations of their own kind. They are, in effect, paying rent in the form of constant vigilance against a constant pressure from outside. The sponge does not protect itself. The sponge does not need to. It has tenants who do. This is the part of the story where the casual reader, who has been told by various sources that pistol shrimp are small, twitchy crustaceans with disproportionate weapons, begins to find that the picture does not quite hold together anymore. To live permanently inside a sponge requires a level of behavioral coordination that no individual animal can provide on its own. A single shrimp cannot patrol all the entrances. A single shrimp cannot maintain defense around the clock. A single shrimp cannot on its own hold a territory against multiple simultaneous intruders. To live inside a sponge, an animal must either be highly aggressive and lucky, or it must have help. And the help that the most successful sponge-dwelling Synalpheus species have arrived at is help of a kind that nobody, until the mid-1990s, expected to find in the sea. The kind of help in question is the kind that ants have, the kind that bees have, the kind that termites have, and the kind that one extraordinary species of subterranean African mole rat has, and that, until quite recently, exactly 4 lineages in the entire history of life on Earth were known to have. The technical word for it is eusociality, and it describes a particular and unusually strict form of cooperative living in which generations of related individuals occupy the same physical space across overlapping life cycles. The work of the group is divided between reproductive and non-reproductive members, and the non-reproductive members spend their lives defending and supporting the colony rather than producing offspring of their own. Eusociality is, by a wide margin, the most complex form of social organization that has ever evolved in any animal. It has been, throughout the modern history of biology, treated as a phenomenon of dry land, a peculiar accident of insects and one strange mammal occurring on a planet whose oceans, vast and ancient as they are, somehow never produced anything equivalent. In a small, dull red sponge attached to a piece of coral rubble in shallow water off the Caribbean coast of Belize, in the year 1996, a marine biologist named Emmett Duffy looked carefully at what he was finding inside the specimens he had been collecting all summer, and he realized that this was no longer true. What was inside the sponge was a colony. There were hundreds of individuals of a single shrimp species packed into the canal system, of every size from newly hatched juveniles to mature adults. There was one female, considerably larger than the others, carrying eggs. There were no other reproductive females. There were no other adults producing offspring. The rest of the animals, including a great many fully grown individuals whose anatomy would in any solitary species have made them sexually mature, were not breeding and never would. They were, the evidence suggested, the offspring of the single reproductive female. They were her children and her children's children, and they had stayed home. The sponge above them, faintly pumping seawater in and out through its dull red surface, betrayed none of this from the outside. A diver swimming past it would have seen only a forgettable lump of substrate in the unhurried language of the older marine biologists. J. Emmett Duffy had been studying sponge-dwelling shrimp in the Caribbean for years before the colony he found in the summer of 1996 changed the structure of the question he was asking. He was a marine biologist at the Virginia Institute of Marine Science, in a research program that focused on the cryptic invertebrate fauna of coral reefs. The small animals that live inside, under, and between the larger organisms most reef biology had been built around. The sponge-dwelling Synalpheus species had been part of that work for a long time. They were known to live in groups. They were known, in some species, to occur at unusually high densities inside their host sponges. What had not been understood, and what the existing observational methods had not been designed to test, was the demographic structure of those groups. Duffy was the first researcher to look at the question with the right tools, in the right place, with the right question already half-formed in his mind from comparative reading he had been doing on the social insects. The species in question was Synalpheus regalis. The name had been given to it earlier in the same year in a separate taxonomic paper by Duffy himself. The Latin word regalis meaning royal, chosen because what he was about to describe in the second paper was a colony structure organized around a single reproductive female. The pairing of the two papers was not coincidental. He had named the species in anticipation of what he was about to publish about it. The colony he documented in the summer of 1996 in a sponge collected from a reef off the coast of Belize contained more than 300 individuals of Synalpheus regalis. Of those 300, exactly one was a reproductive female carrying eggs. The rest, including a large number of fully mature adults of both sexes whose anatomy in any solitary species of pistol shrimp would have made them capable of producing offspring, were not breeding. Genetic analysis using protein markers showed that nearly all the individuals in the colony were close relatives, most of them, in fact, full siblings. They were a single extended family, descended from the one female at the center of the structure, living together inside a single shared host sponge across overlapping generations. The paper was published in the journal Nature on the 6th of June 1996 under a title that did not bury what was being claimed. It was called Eusociality in a Coral Reef Shrimp, and it stated in the abstract that this was the first known case of eusociality in any marine animal. To understand the weight of that sentence, it helps to recall what the word means and where it had been used before. Eusociality is, in technical biology, the most stringently defined form of social organization that any animal has ever evolved. It requires three things, all present together. First, overlapping generations of adults living in the same physical space, so that parents, offspring, and grandchildren are all sharing the same nest at the same time. Second, a division of reproductive labor, so that some members of the group reproduce and others do not by behavioral or physiological mechanism rather than chance. And third, the cooperative care of young, so that the non-reproductive members invest their working lives in the survival of offspring that are not their own. This combination, before 1996, had been documented in exactly 4 lineages of animals across the entire history of life. The ants, which had evolved eusociality once, somewhere around 100 million years ago, and which now occupy almost every land surface on the planet, the eusocial bees and wasps, which had evolved it independently a number of times within the larger group of the Hymenoptera, the termites, which had evolved it independently of the Hymenoptera entirely, from a wood-eating cockroach-like ancestor, perhaps 150 million years ago, and the 2 species of African mole rat, Naked and Damaraland, which had evolved it independently again in underground colonies in the dry grasslands south of the Sahara, sometime within the last 20 or 30 million years. That was the full list, 4 lineages, all of them on land, all of them in groups whose biology had been pored over for decades as the most extreme examples of cooperative living anywhere in the animal kingdom. The ocean, in spite of being older, larger, and biologically more diverse than every terrestrial habitat combined, had produced no equivalent. There had been close relatives, pair-bonded animals, colonial animals, animals that cared for their young at length, but nothing that satisfied the full three-part definition. What Duffy had found in the sponge from Belize satisfied it without ambiguity. The Synalpheus regalis colony had overlapping generations. It had a single reproductive female and several hundred non-breeders. It had cooperative care of the queen's young, who developed inside the same sponge and stayed there into adulthood. The marine equivalent that nobody had ever found, that comparative biology had quietly come to assume did not exist, had been sitting inside ordinary-looking sponges on Caribbean reefs the entire time, and would have continued to sit there indefinitely if Duffy had not thought to look. The follow-up work, much of it conducted by Duffy himself with collaborators across the years that followed, filled in the details. The non-reproductive members of the colony were not idle. They defended the host sponge against intruders, and a follow-up paper published in 2002 with Cheryl Morrison and Kenneth MacDonald showed that they could discriminate with high reliability between fellow colony members and strangers of the same species, responding to familiar individuals with the normal social contacts of colony life and to outsiders with aggressive snaps from the larger males. The defenders were, in effect, a soldier class. The work of guarding the entrance to the sponge was concentrated in their hands, and the queen and the developing young were positioned deeper inside the colony, where the structural protection was greatest. In some species of Synalpheus, the colony has been observed to perform what researchers have called coordinated snapping, in which a sentinel individual produces a series of snaps that recruits other members of the colony to snap in concert, generating a collective acoustic burst that drives intruders away with a force no single shrimp could deliver on its own. The colony, in those moments, becomes a single distributed weapon. The detail of how all this is regulated remains, in many particulars, an open question. The mechanism by which a single female in a Synalpheus colony comes to be the sole reproductive individual is not yet fully worked out. The current evidence, accumulated over decades of work by Duffy and a number of other researchers, including Dustin Rubenstein at Columbia and Solomon Chack at SUNY Old Westbury, suggests a combination of chemical signaling, possibly pheromones released by the queen that suppress reproductive development in her female offspring, and behavioral interactions that maintain her dominance over time. Workers in some Synalpheus species are reproductively totipotent, meaning they retain the capacity to develop into reproductive females themselves if the queen is removed. And in laboratory experiments where queens have been experimentally taken away, a new queen does eventually emerge from among the workers. The colony is not held together by anatomical sterility. It is held together by something more like a continuous signal, broadcast and received, that organizes who reproduces and who does not across what may be hundreds of individuals in a structure no individual member ever leaves. Since the 1996 paper, at least 9 species of Synalpheus in the Western Atlantic have been confirmed as eusocial. Several others are suspected but not yet definitively classified. The geographic range of confirmed eusocial pistol shrimp now extends from the Florida Keys through the Caribbean Sea to the northern coast of South America. They are not rare. In the right reef in the right summer, more than half the sponges of certain species in certain coral rubble zones will be occupied by Synalpheus colonies, sometimes by more than one species of Synalpheus at once, sometimes by colonies in such density that the rubble itself is humming audibly with the collective snap rate of every defender in every sponge for meters in every direction. What all of this means, taken together, is something that the public summary of pistol shrimp biology has not yet fully caught up to. The animal we have spent the previous chapters describing is, in its solitary and pair-bonded forms, one of the more elaborate small animals on the reef. The animal we have spent this chapter describing, in its colonial form, is something else entirely. It is a member of the most exclusive club in animal social evolution. Alongside the ants and the termites and the underground mole rats, it is the only marine member of that club. It is, in some specific structural sense, the ocean's only known eusocial animal. Somewhere on a piece of coral rubble in shallow water, in a sponge no one is paying attention to, a queen Synalpheus regalis is at this moment producing eggs that will hatch into individuals who will spend their entire lives defending her and the sponge she occupies. They will recognize each other. They will recognize her. They will not, in any of their own working lifetimes, breed. None of them will ever leave. The colony will outlast each individual member it produces, sometimes for years, possibly for considerably longer than that. Long enough that the same sponge in the same patch of reef will hold the same continuous lineage across spans of time, during which the surface of the sea above it will have seen storms come and go, wars on distant coasts begin and end, and successive generations of the few biologists who care about these animals quietly turn over in their universities. The shrimp on the supermarket counter and the shrimp inside this sponge are not the same kind of thing. They were never the same kind of thing. The mistake was in assuming they were. Carrie is a small island in the central section of the Belize Barrier Reef, about 20 kilometers off the mainland coast, sitting on a strip of sand and coral rubble barely large enough to hold a research station, a generator shed, and a few palm trees. The Smithsonian Institution has maintained a marine field station on the cay since 1972 in support of a long-running program of Caribbean coral reef research. The structures are modest, the accommodations are modest. The science that has come out of the station in the more than 50 years of its operation has not been modest at all. A substantial fraction of what is known about Caribbean reef cryptofauna, the small, inconspicuous animals that live under, between, and inside the larger reef-building organisms, has been worked out at Carrie Cay or by researchers passing through it. The sponge-dwelling shrimp work has been part of that program from its earlier days. Duffy's 1996 colony was collected from a reef near the cay. The follow-up work in 2002 with Morrison and MacDonald was done on the same reefs. The decades of subsequent research by Duffy and by the network of colleagues and students that built up around the question have been carried out, in many cases, from the same dock, using the same boats, on the same sponges, in the same coral rubble zones, year after year. The cay has become, for this very particular question, the kind of place where the question is asked by going outside, getting into a small boat, anchoring over a reef the researcher has anchored over before, and lifting a sponge that researchers have been lifting for 30 years. When such a sponge is brought aboard and carefully opened in the station's wet lab, the structure of the colony inside it becomes visible in a way that the field never quite reveals. A typical Synalpheus regalis colony in a host sponge of the species Lysodendrix colombiensis occupies the entire internal canal system as a single connected social unit. There are several hundred individuals. There is exactly one ovigerous female, generally larger than every other member of the colony, who can be identified by the cluster of eggs she carries on the underside of her abdomen. There are juveniles of every developmental stage packed into the smaller canals and chambers, often clustered in cohorts of similar size that appear to have hatched together. There are large males, the soldier class, positioned preferentially toward the colony's exterior, near the canal openings that connect the interior of the sponge to the surrounding seawater. There are intermediate workers of indeterminate eventual role doing the routine business of moving through the canals and processing food. And in many colonies there are early-stage males whose physical maturity has plateaued at a sub-reproductive level, who never become full-sized soldiers and never reproduce, a finding that has emerged only in the more recent literature and whose biological significance is still being worked out. The colony, taken as a whole, has an architecture. The queen is not randomly placed within the sponge. She is reliably found in the deepest, most protected interior chamber accessible by the canal system, in the part of the sponge furthest from any opening to the outside. The soldiers are not randomly distributed either. They are concentrated near the entrances where threats arrive. The juveniles cluster in regions of intermediate depth, close enough to the queen to receive whatever chemical or behavioral signaling she provides, far enough from the openings to be protected from the direct passage of foreign water. Nobody, as far as the literature shows, has yet identified the mechanism by which the colony maintains this spatial organization. Whether the positioning is the result of active sorting by individuals, of chemical gradients within the sponge, of pheromonal cues from the queen, or of some combination of these is not yet known. What is known is that the organization is consistent and that it persists across the working life of the colony. The behavioral work that has been done inside intact colonies, mostly in laboratory tanks that approximate the interior of a sponge, has filled in a picture of the moment-to-moment social life that the field collections alone cannot show. The most striking finding, in some ways, is also the simplest. The colony members can tell each other apart. In a series of experiments conducted in the late 1990s and again in the 2002 follow-up paper, Synalpheus regalis individuals removed from their natal colony and placed in contact with both familiar and unfamiliar conspecifics behaved differently toward each category. Familiar individuals, siblings and parents from the same colony, received the gentle contacts of ordinary colony life. Unfamiliar individuals, even of the same species, even of comparable size, received aggressive snaps from the larger males at significantly higher rates than the controls did. The shrimp were not simply discriminating between Synalpheus and not Synalpheus. They were discriminating between members of their own colony and outsiders. The recognition was specific, it worked, and it worked reliably. The mechanism, as in so many other parts of this story, is most likely some combination of contact chemoreception and waterborne chemical cues, but the molecular details have not yet been worked out. What such recognition makes possible is something that no solitary or pair-bonded pistol shrimp can do. A colony with several hundred members, all of whom can identify each other, can coordinate. The most visible form of coordination is the behavior that researchers have called collective or coordinated snapping, in which an intrusion at the entrance to the sponge triggers an escalating response across the colony. A sentinel individual at the threatened opening produces a series of rapid snaps. The snaps propagate through the canal system as both acoustic and pressure signals. Other defenders, hearing or feeling them, move toward the entrance and add their own snaps to the response. Within a small fraction of a second, a colony can move from passive occupancy to a coordinated barrage of dozens of simultaneous snaps directed at a single intruder. The intruder, in nearly every documented case, retreats. The colony, having repelled the threat, returns to its baseline activity. There is a useful comparison to be drawn here, although the comparison has to be made carefully. In ant colonies, when a nest entrance is breached, the response is similarly coordinated. A chemical alarm signal recruits defenders, and the defenders converge on the breach. The biology of the recruitment is different in the two cases. Ants use volatile alarm pheromones. Synalpheus use acoustic and pressure signals propagating through water and the sponge tissue, but the function is recognizable across them. A distributed group of individuals responds to a local threat with collective force, and the threat is dealt with at a scale no individual member of the group could achieve. The fact that this convergent solution has arisen independently in two animal lineages as different from each other as a Caribbean shrimp and a temperate ant suggests that something deep in the logic of cooperative defense favors it, regardless of the substrate the cooperation runs on. The longer-term behavior of the colony across months and years rather than across the moments of a defensive response is harder to study but no less interesting. The available evidence suggests that colonies can persist across multiple queen lifetimes. When a queen ages and her reproductive output declines, or when she is lost to predation or disease, a replacement appears from among the workers, possibly a daughter, possibly a sister, possibly a more distantly related female who happens to have retained the reproductive plasticity. The work of Solomon Chack and his colleagues, published in the late 2010s, has shown experimentally that female workers in at least one Synalphia species, S. elizabethae, are reproductively totipotent. That is, in the absence of a queen, their suppressed ovarian development can resume and they can transition to a fully reproductive state. The transition does not appear to involve physical aggression among workers competing for the queen role. It is mediated instead by something quieter and more pheromonal, in which the loss of the previous queen's signal allows the next viable female in the colony to take her place. What this means in the long arithmetic of a sponge is that a colony is not the lifetime of its queen. The colony is the lifetime of the sponge. A Synalpheus regalis lineage can occupy a single host sponge across multiple queen generations, with successive queens succeeding one another in the deep chamber, while the rest of the colony reorganizes around each succession. As long as the sponge survives, and as long as the colony retains the capacity to produce a new queen when the previous one is gone, the social structure continues. The Smithsonian work at Carrie Cay has tracked individual sponges in known locations across more than 2 decades, and many of those sponges have continued to hold continuous colonies of the same Synalpheus species throughout that span. The reef has changed. The seawater has warmed by a measurable fraction of a degree. Hurricanes have passed over the cay. Researchers have arrived as students, become postdoctoral fellows, become principal investigators, and retired. The sponges have stayed where they were, and the colonies inside them have continued to do, day after day and night after night, exactly what they were doing when Duffy first opened one in 1996. Inside any one of those sponges at this moment, several hundred related individuals are moving through a system of canals they have known their entire lives. A queen, at the center, is laying eggs that her sisters and daughters will defend. A handful of large males near the openings are listening through the water for the first sign of an intruder. The colony has no name in any human sense. The queen has no name. The individuals doing the defending have no names. There is only the colony and the sponge and the reef around them, all of which have been here for considerably longer than any of the people who have ever looked carefully at what they contain. A hydrophone is, in its simplest form, an underwater microphone. It is a small sealed cylinder of metal and ceramic attached to a long insulated cable designed to detect the pressure variations in seawater that travel through it as sound. Lowered carefully from a small boat into the shallow water of a tropical reef, with the engine off and the boat drifting on a calm afternoon, a hydrophone produces, through a pair of headphones plugged into its amplifier, the closest thing the people on the boat will ever come to hearing what the reef sounds like on its own time, without them. The first impression for most people who hear it for the first time is that the equipment has failed. The signal in the headphones is so dense, so continuous, and so unlike any sound the listener has expected the ocean to make, that it presents at first as static or interference. Only after several seconds, with the volume adjusted and the ear settling, does the texture of the sound resolve into what it actually is, a steady, layered, irregular crackling, like fat sizzling in a heavy pan or like a slow rain falling on broad, dry leaves. There is no melody. There is no rhythm in any musical sense. There is only the sound itself going on and on, made by thousands of small animals on the seabed below the boat, each contributing one snap every few seconds, all of it summing all of the time to the background hum of the entire shallow tropical ocean. The systematic study of this sound has been a relatively recent development in marine biology. The wartime acoustic teams of the 1940s had identified that snapping shrimp were the source, but they had been interested in the noise as a problem to be solved or avoided, not as a phenomenon to be understood on its own terms. The shift, when it came, was a function of new tools. Inexpensive, robust hydrophones became widely available in the 1990s. Long-duration underwater recording systems became practical in the 2000s. By the 2010s, an entire subdiscipline of marine biology, sometimes called soundscape ecology or bioacoustics applied to ecosystems, had grown up around the question of what reefs sound like, how that sound varies, and what the variation reveals about the underlying biological state of the system. The numbers that have emerged from this work are, even to researchers who have been doing them for years, fairly staggering. In a healthy coral reef in the Western Atlantic, a single hydrophone at a fixed depth can register snap rates between 1,500 and 2,000 individual snaps per minute during the warm summer months, dropping to perhaps 1/100th of that in the colder seasons. Scaled across the surface area of a typical reef, these numbers translate into tens of millions of snaps per hour, in every reasonably populated stretch of shallow tropical seabed on the planet. The sound is the dominant biological signal in the high-frequency bands of the underwater soundscape, well above whatever fish vocalizations and surface noise are also present. If you were to filter out everything except the snapping shrimp in most reefs, you would lose only a small fraction of the overall acoustic energy. The reef, acoustically speaking, is mostly shrimp. What that fact means for the rest of the reef ecosystem turns out to be more interesting than anyone expected. In the mid-2000s, a series of studies began appearing, first in Australia and the Pacific, then in the Caribbean. That demonstrated that the larvae of various reef-building corals were not arriving at suitable settlement sites by chance, or by chemistry alone, or by drifting along passively until they happened to touch something solid. They were, to a significant extent, listening. The larvae of stony corals, in their first few hours of swimming life, are sensitive to underwater sound. Given a choice between water that carries the soundscape of a healthy reef and water that does not, the larvae actively swim toward the noise. The healthy reef, as far as the larvae are concerned, sounds like a place worth settling on. The degraded reef, which has lost most of its snapping shrimp along with the rest of its dense invertebrate fauna, sounds like nothing, like an open sandbed, like a dead patch. The most extensive single test of this finding was published in 2024 in the journal Royal Society Open Science by a team led by Nadej Aoki and Aaron Mooney of the Woods Hole Oceanographic Institution. The team built a custom solar-powered acoustic playback system, deployed it at degraded reef sites in the United States Virgin Islands, and broadcast the recorded soundscape of a healthy nearby reef into the surrounding water. The settlement rates of larvae of the brooding coral porites asteroids at the speakered sites were significantly higher than at unspeakered control sites at the same locations. The result was not subtle. The corals could hear the difference. They preferred the sound of a working reef, and the playback of that sound was enough to bring them in. Whatever else one might say about the snapping shrimp on the reef floor, they are, among their many other roles, a recruitment beacon for the corals that will eventually grow above them. The shrimp have been calling young corals home for considerably longer than there has been a human present to record it, and the recordings are now being used in early-stage restoration projects as a tool to bring the corals back to places where the original calling has gone quiet. There is a darker version of the same finding, which has emerged from the parallel work of Aaron Mooney's lab and a number of collaborators on the question of how the snapping shrimp themselves respond to changing ocean conditions. The shrimp are cold-blooded animals. Their metabolic rates, including the rate at which they fire their snapping claws, are determined in significant part by the temperature of the water around them. In laboratory experiments comparing the snap rates of Synalpheus colonies at different controlled water temperatures, the differences are dramatic. At 10 degrees Celsius, a typical colony might produce something on the order of 50 snaps per day. At 30 degrees Celsius, the same colony produces roughly 10 times that. The relationship is not linear at the extremes, but across the range of temperatures relevant to a warming tropical ocean, the trend is clear. Warmer water produces more snapping, and more snapping produces a louder ambient soundscape. The work was presented at the 2020 Ocean Sciences meeting, has been picked up by subsequent studies in the years since, and the broad conclusion has held up. The reef, as the ocean warms, is going to get louder. The shrimp themselves are likely to be fine, at least within the range of temperatures that are currently projected. What this will do to the larger acoustic ecology of the reefs, to fish that communicate, to mammals that navigate by sound, to the larvae that are themselves listening for cues, is not yet known. A separate strand of research, less prominent but no less consequential, has been working out how much of the actual physical structure of a reef the snapping shrimp are quietly maintaining. Pistol shrimp are bioturbators. That is, they are animals that, in the course of their daily lives, move sediment around. The construction and constant maintenance of burrows by the solitary species and the slower but cumulatively substantial reshaping of host sponges and coral rubble by the colonial species adds up across the surface area of a typical reef to a meaningful turnover of the seabed substrate. Recent work using acoustic monitoring to estimate snapping shrimp density, including a large-scale AI-assisted soundscape analysis published in 2025, has begun to quantify the relationship between shrimp activity and broader reef-scale processes. The shrimp are not just making sound, they are also, by the simple physical work of their daily lives, helping to keep the seabed beneath the corals biologically active rather than letting it compact and stagnate. A healthy reef has a living sediment layer beneath it. The pistol shrimp are, in significant part, why. What all of these findings combine to suggest, taken together, is that the snapping shrimp are not a curiosity layered on top of a reef ecosystem that would basically function without them. They are part of how the reef works as a system. They are part of how it recruits new corals. They are part of how it processes its sediment. They are part of how it sounds, and the sound they produce is itself a signal that other organisms, including the corals, actively use. If they were quietly removed in some thought experiment from a stretch of reef tomorrow, the reef would not just become quieter. The reef would, over the following years and decades, begin to fail in ways the absence would not immediately make obvious. The recruitment signal would weaken, the sediment would compact, the fauna that depended on the burrows and the colonies and the constant background fact of these animals doing their work would begin to thin. The acoustic monitoring researchers, listening for the snap rate as a proxy for ecosystem health, would notice the silence first, and they would know what it meant. A great deal about how this works at the finest grain remains uncertain. the snap rate's response to subtle environmental changes is not fully mapped. The relationship between shrimp population density and coral recruitment success has been established but not yet thoroughly quantified across different reef types. The role of the snapping shrimp soundscape in fish communication is suspected to be substantial, but is, in most studies, treated as background noise rather than as a signal to investigate in its own right. What is clear, and what the work of the last 15 years has made unambiguous, is that the reef beneath the boat, the reef the hydrophone is listening to, is in a steady, working state that depends, more than anyone had appreciated until recently, on the continuous low-level acoustic and physical contribution of an animal almost no one outside of marine biology has ever heard of. The boat drifts. The hydrophone, suspended a few meters below the surface, continues to transmit. In the headphones, the sound goes on without pause, layered and irregular and dense, the same sound that has been continuously produced by these animals across the same kinds of reefs for considerably longer than there have been hydrophones to record it, or boats to drift over them, or people to listen in. In April of 2017, 3 taxonomists published a short technical paper in the journal Zootaxa describing a new species of pistol shrimp from the Pacific coast of Panama. The paper was 8 pages long, and most of it consisted of careful comparative measurements of the new species against its closest known relative in the Western Atlantic. The morphological differences between the two were, as the authors openly acknowledged, subtle. Slightly different proportions of a particular segment of one of the claws, slightly different armature on the dorsal surface of another, a slightly different relative length of one of the antennal structures. To the eye of anyone who is not a specialist in this particular family of shrimp, the two species would be indistinguishable. The case for separating them as distinct species rested mostly on the genetics. The two populations had been isolated from each other for somewhere between 6 and 8 million years, since the rising of the Isthmus of Panama closed the seaway that had once connected the Caribbean and the Eastern Pacific, and in that time they had diverged in their mitochondrial DNA by more than 10%, well past the threshold at which most crustacean taxonomists would treat them as separate species. What made the paper notable was not the morphology or the genetics. Both were competent work, the kind of thing that gets published in Zootaxa and similar journals every week of the year. What made the paper notable was the name. The authors had called the new species Synalpheus pink floydii. The etymology section of the paper, terse and technical in the manner of formal taxonomic writing, gave the reason. The species was being named after the British rock band Pink Floyd, in recognition of the unusually intense pink-red coloration of its major snapping claw. A suggested vernacular name was offered in the same section, the Pink Floyd pistol shrimp. The senior author on the paper, Sammy de Grave, was the head of research at the Oxford University Museum of Natural History. The other 2 authors were Arthur Anker, a Brazilian-based specialist in Alpheid shrimp taxonomy with a remarkable record of new species descriptions, and Kristin Hultgren, a marine biologist at Seattle University who had been working on the social evolution of sponge-dwelling Synalpheus for years, and who had been part of the Duffy network. In the press materials released by Oxford to accompany the publication, de Grave explained the naming choice in a small statement that has since become one of the more widely quoted lines in modern taxonomic writing. He had been listening to Pink Floyd since 1979, when The Wall was released and he was 14 years old. He had seen the band play live multiple times in the years that followed, including the 2005 Live 8 reunion in Hyde Park. The description of this new species, he wrote, was the right opportunity to finally give a nod to his favourite band, the right scientific occasion for which he had been holding the gesture in reserve for 38 years. There is something about the line that is worth pausing over. Most of taxonomy is invisible work. The naming of a species, the formal description, the lodging of a type specimen in a museum collection, the publication of the diagnostic features that distinguish it from its closest relatives, is one of the slowest and most patient activities in modern biology, conducted by a small number of specialists whose entire careers might involve the formal description of a few dozen new species, often of animals nobody outside the discipline has ever heard of. The work is essential. Every other claim biology makes about a species, its biogeography, its ecology, its evolutionary relationships, its conservation status, depends on the species having been formally described in the first place. But the work is also, by the standards of most other sciences, quiet. The recognition that comes from it is small. The audience is largely other taxonomists. What de Grave's gesture acknowledged, perhaps without intending to, is that the people doing this work are still people. They have lives outside of the laboratory. They listen to music. They were teenagers once, in particular decades, listening to particular records that meant something to them at the time. And the meaning of those records does not entirely leave when the listener becomes a taxonomist at Oxford. A new pistol shrimp from the eastern Pacific with a strikingly pink claw gave one such taxonomist the chance to put one of those records permanently into the scientific literature, alongside the species' formal Latin description and morphological measurements and DNA sequence data. The shrimp itself, swimming about in its native waters off the coast of Panama, has no idea. The shrimp does not know about Pink Floyd, or The Wall, or the Live 8 reunion in Hyde Park, or Sammy de Grave. It carries the band's name regardless in the formal record of modern biology, for as long as that record is kept. Synalpheus pink floydi is a sponge dweller, like most members of its genus, and a member of the broader Gambarelloids group that includes most of the well-known social species. Whether it is itself eusocial or pair-living has not yet been definitively determined as of the time of this writing. The social biology of the Eastern Pacific Synalpheus is much less studied than that of the Caribbean species, and the new species colony structure has not been thoroughly characterized. Its closest known relative, Synalpheus antillensis, was described from the Caribbean in 1909 by the French carcinologist Henri Coutier, working in an entirely different era of taxonomic practice, more than a century before the Oxford team's revision. The pair of them, the long-known Atlantic species and the newly named Pacific one, separated by a few million years of evolution and a closed isthmus, now stand together in the published record as cryptic sister species, with the older name dating to the year before the start of the First World War, and the younger one to the spring of a recent year in which most of its eventual readers were already alive. The naming of Pink Floyd's shrimp is the most attention-grabbing example of what is, in the broader picture, a much larger and quieter ongoing project. The full known diversity of the family Alphidae now stands at something on the order of 1,100 described species, distributed across 38 or so genera, in every tropical and subtropical sea on the planet. The two largest genera, Alpheus and Synalpheus, between them account for the great majority of described species, with Alpheus alone now numbering over 330 species and Synalpheus over 160. New species are described, on average, at a rate of roughly 10 to 20 per year, and the consensus among the specialists is that a substantial fraction of the actual diversity in the family is still undescribed. Arthur Anker, the second author on the Pink Floyd paper, has personally described more than 100 new species of Alphidae over the course of his career, and is generally credited with being one of the most productive carcinologists working today. Even at his pace, the full inventory of the family is not expected to be complete for decades. Part of the difficulty is that pistol shrimp are difficult animals to find systematically. They live in burrows, in coral rubble, inside sponges, inside the tunnels of other invertebrates, in caves, in mangroves, in places where the act of finding them requires hours of careful disassembly of the substrate they are hiding in. Many species are tiny, under 2 centimeters in length, and morphologically conservative, meaning that the differences between closely related species can be small enough that a single specialist may need to compare a dozen specimens under a dissecting microscope to decide what is what. The genetic tools that have transformed the recent work are themselves only a few decades old, and their application to Alpheid taxonomy has been concentrated in a small number of laboratories. The result is that the field is, in a real sense, still in its early stages. New species continue to appear from places that have been worked over by previous generations of specialists, simply because the new generation is looking with finer tools. Some of the more recent finds have come from deep water and from caves, habitats that older expeditions did not sample well, and that newer ones have begun to investigate more carefully. Others have come from re-examination of museum specimens that were collected decades ago and labelled with what we now understand to have been the wrong species name. The Pink Floyd shrimp itself was, in part, a re-examination of populations from the eastern Pacific that had previously been assumed to be Synalpheus antillensis until the genetics suggested they were not. There are almost certainly more such corrections waiting in the world's museum collections. The work of going through them, specimen by specimen, drawer by drawer, is unglamorous and underfunded, and continues anyway, in the laboratories of the few researchers who have made the family their life's work. Somewhere in the warm shallows off the Pacific coast of Panama tonight, in a sponge nobody is paying attention to, a small shrimp with a bright pink claw is going about its working life, patrolling its host, defending its territory, snapping occasionally at intruders or at prey. It belongs to a species that is, by the standards of formal biology, almost brand new, described less than a decade ago with most of its biology still uncharacterized, holding a name that was given to it by a man who first heard the band it is named after when he was a teenager and the album was new. The shrimp will live, by the usual estimates for its genus, for perhaps 3 to 4 years. It will not know that it carries the name of a band, or that the band's senior member it was named in honor of will outlive most of the individual shrimp of its species by a substantial margin. The name stays with the species regardless, attached to it in the published record, available to any biologist who looks the species up. The shrimp goes on snapping in water that has been warm for as long as there has been a Pacific Ocean, in a sponge that does not care what anyone above the surface has decided to call its tenant. In the summer of 2012, Emmett Duffy and a small team of collaborators returned to the reefs around Carrie on a routine sampling trip. They had been making trips like this one for years. The methods were the same. The sponges they collected were the same species, from the same coral rubble zones, in the same shallow water they had been working in since the early 1990s. The team knew, going in, what the colonies inside those sponges should look like. They had been pulling colonies from these reefs for nearly 2 decades, and the demographic structure was well established. There should have been hundreds of individuals in many of the host sponges. There should have been queens carrying eggs. There should have been the dense packed canal architecture of working eusocial colonies of 3 or 4 well-known Synalpheus species, occupying the rubble in the high densities the team had come to expect. What they found, when they opened the first set of sponges in the wet lab, was something else. The colonies were smaller. The queens in many sponges were missing. The colonies that did still have queens were noticeably less populous than they should have been, and a significant fraction of the sponges they collected, sponges of the right species in the right places, the kind of sponges that should have contained colonies of one of the eusocial Synalpheus species the team had been tracking for years, contained no shrimp at all. 3 of the 4 eusocial synalpheus species that had been numerically dominant on these reefs since the early 1990s were, on this trip, locally extinct. The team did not find them. They did not find any individuals of those species in any of the sponges they sampled, in any of the locations on the reef they had worked in previous years. The species had not relocated. The species had not retreated to deeper or more sheltered water that the team could check. They were simply gone. The finding was published in 2013 in the open access journal PLOS 1 in a paper titled Decline and Local Extinction of Caribbean Eusocial Shrimp. The paper documented the disappearance of the 3 species from Carrie Cay, alongside parallel evidence from sites in Jamaica and Panama showing similar declines, smaller colony sizes, an increase in the fraction of colonies that were queenless, and a general thinning of the eusocial populations that had, in some places, dominated their rubble communities for decades. The most likely cause, the authors suggested, was the concurrent decline of the host sponge species that the eusocial shrimp depended on. 2 specific sponge species, both of which had been important hosts for the now vanished shrimp, had themselves declined steeply on these reefs over the previous decade. The shrimp could not live without the sponges. When the sponges thinned, the shrimp went with them. The non-eusocial pair-forming synalpheus species in the same area had held up better, the paper noted, because they were less specialized in their habitat requirements and could occupy a wider range of hosts. In the years that followed, several of the same researchers continued the work. A demographic modeling study published in 2020 with Solomon Chack and Dustin Rubenstein among the authors used the longer time series to ask whether the declines at Carrie Cay represented a permanent local extinction or a cyclical population bottleneck of the kind that even healthy eusocial populations can occasionally pass through. The modelling, on the balance of the available evidence, supported the more sobering reading. Eusocial synalpheus populations may be inherently more demographically fragile than pair-living relatives, the authors argued, precisely because they place all their reproductive eggs into a single queen and a single host sponge. When a host sponge dies, the colony dies with it. When a region loses its host sponges faster than the surviving colonies can disperse to new ones, the whole eusocial population in that region can collapse quickly, completely, and without a clear pathway back. The cyclical interpretation, in which the colonies would eventually return to the cay on their own, could not be ruled out. But neither could the more permanent reading, in which what the team had lost in 2012 was lost for the foreseeable future of the human horizon. The reefs at Carrie Cay continue to be monitored. The Smithsonian Station continues to operate. The pair-living synalpheus species and the solitary alpheus species and the many other small inhabitants of the rubble continue to do their work in the canals of the surviving sponges. The reef's overall acoustic activity remains substantial. The snap rate on a calm evening with a hydrophone in the water is still dense enough that the headphones sound like fat in a hot pan, the way they always have. To an unfamiliar listener, the reef would still pass for a working tropical reef, full of the sound of small animals going about their lives. The careful reader of the soundscape, however, would notice that the texture is different from what it was 20 years ago, that something has thinned, that some of the lower harmonics of the collective hum are no longer being produced by the same density of large coordinated colonies that used to produce them, that the reef is the same reef and is also not the same reef. This is, in some essential sense, the condition of every shallow tropical reef on the planet right now. The pistol shrimp themselves, as a family, are not in immediate danger. They are widely distributed, biologically resilient at the level of the family as a whole, and represented by hundreds of species across every warm sea on Earth, many of which are doing well. The conservation concern, where there is one, is specific to the most specialized of them, to the eusocial synalpheus species, dependent on particular sponge hosts in particular reef systems, vulnerable to a chain of habitat losses that does not need to target the shrimp directly in order to remove them. The shrimp themselves are not the most fragile part of the system. The system is fragile, and the most specialized of the shrimp are the part of it that, when the larger structure starts to fail, falls first. There is a longer view available here that is worth taking before this account ends. The family Alphidae, in the broad sense, is approximately 150 million years old. It first appears in the fossil record in the warm, shallow seas of the late Jurassic, in rocks laid down at a time when the present-day continents were still bound together as the supercontinent of Pangaea and were just beginning to come apart. The dinosaurs were the dominant vertebrates on the land surfaces above those seas, in the middle of their long reign. The corals that built the reefs in which the early Alphids lived were of completely different lineages from the ones that build the reefs of today. The modern scleractinian corals had only recently evolved and had not yet risen to ecosystem dominance. Mammals existed but were small and unimportant. The Atlantic Ocean did not exist in any form a modern atlas would recognize. The Pacific was a vast sea covering most of the planet's surface, much larger than it is today, with currents and shorelines and biological communities that no human has ever seen. Through all of that, through the breakup of Pangaea, through the end Jurassic disturbances, through the rise and fall of the Great Cretaceous coral reefs, through the asteroid impact that ended the Cretaceous and most of the lineages alive at the time, through the long warm Eocene and the cooling Oligocene and the alternating glaciations of the Pleistocene, through the closing of the Tethys Ocean and the opening of the modern Atlantic and the slow assembly of the present-day map of the world, the snapping shrimp continued. The corals changed, the reefs changed, the other inhabitants of the reefs changed, repeatedly and on enormous scales. The snapping shrimp, in the rubble at the base of whatever reef happened to be there at the time, continued to snap their claws into the water and fire small bubbles and bring down small prey and dig small burrows, and eventually, somewhere on the way, to invent sponges as housing and queens as colony centers, and a coordinated defense involving collective bursts of cavitation. The lineage has been doing this through extinctions that took out vastly larger and more visible animals. It will, on every reasonable estimate, continue to do it through whatever the next several million years bring in some shallow tropical sea somewhere on whatever version of the planet exists by then. What is more uncertain is whether any one of the specific species that constitute the lineage at this particular moment, the named, described, currently living species of pistol shrimp, of which there are around 1,100, including the 4 that quietly disappeared from Carrie Cay a little over a decade ago, will still be on the rolls 100 years from now. Some of them will. Some of them, given the trajectory of the reefs they depend on, will not. The lineage outlasts the individual species the way the species outlasts the individual animal. The family is older than any specific reef on the planet and will be younger than the reef that exists after this one. Inside that long perspective, individual losses are real but not catastrophic to the lineage. From inside the lineage's own time, the disappearance of 3 eusocial species from a particular cay in 2012 is a small local event in an animal group that has seen many local events of many kinds. This is, in a way, the most honest emotional register to land on. The pistol shrimp does not need our concern in the way some other animals do. It does not need our protection in the way some other animals do. What it does need, if we are paying attention to what it has been doing for the entirety of human history and a great deal of time before that, is something more like our notice. The animal has been performing remarkable physics in shallow water on this planet for longer than there have been any animals capable of recognizing the physics for what it is. We have, in the last few decades, finally caught up to some part of what the snap is, what the sponge contains, what the soundscape means, why the orbital hood is there, why the queen sits where she does. We have not, even now, caught up to all of it. The animal has been ahead of us for the entire history of marine biology, and it will, on every available indication, continue to be ahead of us indefinitely. What is happening tonight in shallow water along every warm coastline on the planet, in coral rubble and inside sponges and in the sand near the entrances of small burrows nobody is paying attention to, is the continuation of a working biology that has been continuous since the late Jurassic. Hundreds of millions of pistol shrimp in trillions of individual claws are at this moment going through the same set of small motions they have been going through across every minute of every night for a very long time. Many of them, right now, are cocking their claws against small invisible latches inside the joints. Many of them are letting those latches go. Many of them, in the half-second after, are watching the small bubble they have just created collapse on itself, deliver its shockwave forward into the dark, briefly fire a tiny flash of light that no eye in the water will see, and produce, at the precise moment of its dying, a single sharp pop that, multiplied by the hundreds of millions of other shrimp doing the same thing in the same kind of water in the same long night, makes up the largest and oldest continuous biological sound on the surface of this planet. If you were to listen with no hydrophone and no equipment of any kind, in absolute quiet, on a dark beach beside a calm tropical reef somewhere in the world tonight, you would not hear any of it. The sound stays under the water. It stays inside the sand. It is not in any way that human ears can register a sound the world has been able to receive. But it is happening, and it has been happening in just this way, for far longer than there have been ears at all. Somewhere out there tonight, in water you will probably never see, a pistol shrimp the size of your finger is pulling its claw back, holding it for a long second and letting it fall. The water in front of it boils for a microsecond. A small star catches and goes out. The shrimp turns inside its burrow, settles, and waits for the next thing to come close enough to be worth the snap. It does not know we are here. It does not need to. The work it is doing tonight is the same work that has been done in these same kinds of waters for 150 million years, and the work will continue without commentary after we have all gone to sleep. Good night.